Okay, so let's begin. Uh, we are doing machine translation. We would like to do language divergence to an extent and go in depth into machine translation evaluation. And that will lead us to hypothesis testing. All of these are very important topics, not only for machine translation, but for whole of NLP. Now, I'm traveling. That's why today's class is online on Teams. Now, as is usual for our class, we do a one slide recap of the week, which is past, the week of 2nd September. So in that week, Saurav uh, took the first lecture, and then I took the Thursday's lecture. What was covered is, first of all, machine translation, its definition, and paradigms. The fact that there is rule-based machine translation, followed by statistical machine translation, then neural machine translation. And we know that machine translation is difficult, uh, of course, in general for ambiguity, as is true of any area of natural language processing. But in case of machine translation, there is a special task which needs to be addressed. That is language divergence. Okay, how the same thought is expressed in different ways in different languages. We know that in Indian languages, the verb goes to the end. In Arabic, the verb sits in the front. So that's an example of language divergence between Arabic and Indian languages. Vokwa triangle, any student of machine translation has to remember this as a foundational concept. So in Vokwa triangle, we have the left-hand side, which corresponds to analysis of the input text, and the right-hand side, which corresponds to generation of the target text. So if the input is an English sentence, and if we do some processing on the English sentence, we can have, we are moving up the left-hand side to some distance. Now, you can see there is this syntagmatic level, which corresponds to identifying the part of speech tags and the syntactic tree of the source sentence. Then that tree is processed. That's called syntactic transfer. And the parse tree of the target language is obtained. And from that, we obtain the sentence by traversing the parse tree, the syntactic tree of the target language. C structure corresponds to constituent structures, and we obtain the target language sentence from the constituents in the parse tree. An interesting fact here is that we do have descending transfers. So this means that I will not use the transfer path at all, but generate the target language sentence directly from the parse tree, which I had obtained for the source language. So the transfer means you transform the result of analysis on the source side to go to the target side. Now, in this case, if the source language, target language sentence is directly produced, then there is no transfer stage. There is no transfer stage which is parallel to the base of the triangle, but direct transfer, okay, direct descending. And it's called descending because there is no particular representation for the source sentence. The source sentence is produced word by word or phrase by phrase directly from the parse tree of the source sentence, and the target sentence is produced directly. What will be an example of this? An example of this will be if the two languages are very close to each other, source language and the target language, let's say Bengali and Assamese, or even Hindi and Urdu, let's say. Now, the parse tree of the source language is uh, is is uh, is producing the constituents, and from there I can directly go to the target language. Let's say from Bengali parse tree, I directly produce the Assamese sentence without first obtaining an Assamese parse tree. Why so? Because the Assamese parse tree will be identical to Bengali parse tree, except for words being some of the words being different in Assamese. Then the question that will arise is that then why at all do the analysis on the source language side? If the Bengali word substituted by Assamese word produces the Assamese sentence, why do any parsing at all? Well, the parsing is required to identify the constituents very clearly, and we'll think about such examples. I do not have it offhand. The constituents are identified very clearly, and from the constituents, we directly obtain the words of the target language. So, for example, it is possible that a group of words gives rise to a single word in the Assamese language. A group of words in Bengali produces a single word in Assamese. Okay, so the overall syntactic structure is same, except that some of the words in Bengali are collapsed into one single word in Assamese. So this would require identifying constituents and collapsing that constituent into one word. So there are the whole Vakwa triangle is a gold mine, giving lots of food for thought. Okay, and it is very instructive for all of you to sit down with the triangle and take language pairs and see if you can if you are required to do ascending transfer. In ascending transfer, we go from one level of analysis to a much higher level on the target side. We are required to go and then produce the generated sentence from that tree, from that representation. So these require deep insight into how languages work and what is the pair of languages. But it's an extremely beneficial exercise to give you insight into what computational power is required to do machine translation. So Vakwa triangle indeed has been a very foundational concept in machine translation, and its value has not eroded over time. The concept has remained as relevant as it was in 1960s when this was proposed by a physicist from France called Vakwa. The tip of the triangle is the deep understanding level. So this means that the source sentence is completely disambiguated into a representation. And from that representation, we produce the generated target language sentence. So this is going from zero ambiguity object to target language sentences, which may have ambiguity. Of course, any natural language has ambiguity. The deep understanding level is not a natural language. It is a deep semantic representation with all ambiguity removed. So our NLP journey in CPIL started with a project called UNL, Universal Networking Language. So that project attempted to create deep understanding level representations for 15 languages of the world, of which Hindi was a part. And the deep understanding level was UNL graph, which I hope to show you at some point of time, where all disambiguation is made. Now, one question that might arise is that why not always go to the deep understanding level and then produce the target language sentence? The answer is it is not necessary. If the languages are close to each other, then we can remain even at the graphemic level without any analysis on the source language sentence and do phrase and word substitution, go to the target language side. And since traversal over the left-hand side is an exercise in disambiguation, it means we are doing disambiguation. Now, depending on the pair of language, disambiguation may not be necessary. So my favorite example is if we take this Hindi sentence, आपको मुझे चाय पिलानी पड़ेगी. This needs disambiguation. It is not clear who is giving tea to whom. But if the target language can tolerate that ambiguity and retain that ambiguity, we don't need that disambiguation. For example, in Bengali, আপনাকে আমায় চা খাওয়াতে হবে. This is not, this is ambiguous and but a translation of the Hindi sentence. So this disambiguation is not required. Therefore, that's there are multiple levels of transfer throughout the triangle. Again, showing a very conceptually rich situation where we produce the translation after some transfer and natural language generation. Now, all of us should remember that Vokwa triangle is relevant even in the context of LLMs and generative AI. LLMs and generative AI are very successful in terms of natural language generation. So the LLM generative capability should be used on the right-hand side of the Vokwa triangle. So Vokwa triangle, you are requested to look at and peruse and think deeply about. So ATG framework is a contribution of the Vokwa triangle. It gives a very nice framework to understand the whole translation business. ATG, analysis, transfer, generation, analysis on the source side, transfer from the result of analysis to the target side, and the representation on the target side converted to the generated sentence in the target language. So this is ATG. Now, ATG is implicitly, explicitly done in the encoder-decoder network, which is the hallmark of neural machine translation. Saurabh had discussed this in his lecture. So what happens is that the source language sentence is encoded, okay? And from that encoded by auto-regression, word by word, the target language sentence is produced. I read the book, मैंने किताब पढ़ी. This is a translation. So this encoder-decoder framework is very simple to understand. Now, of course, there are lots of subtleties and lots of hidden depth, hidden traps there. First and foremost, for a very long sentence, the encoded representation is not enough. You need what is called the self-attention mechanism there. And for a long sentence, the target language sentence generated needs cross-attention. And auto-regression anyway takes care of the sentence which is generated so far. But this encoder-decoder framework is really the basic tool for neural machine translation. Now, data-driven machine translation always makes use of this noisy channel model equation. E bar equal to argmax over all possible E, probability of E given F. So probability of the source sentence, probability of the target sentence E, given the source sentence F. Now, you might wonder why E and F, why not X and Y and so on. The reason is historical. All these data-driven machine translation papers, they tried their framework on French-English translation. French input, English output. Okay, French to English. So F stands for French, E stands for English. That is the historical reason. But of course, now this particular equation is used for any pair of languages, English, Hindi, Bengali, Hungarian, French doesn't matter. So this is the one slide recap of what was done in the last week. We would like to go deeper into some topics now. So machine translation, just to remind ourselves, takes the source text, goes through the machine translation system, produces the target text. Then paradigms of machine translation, we see are RBMT, rule-based machine translation, EBMT, example-based machine translation, NMT, neural machine translation, SMT, statistical machine translation. So rule-based machine translation is handmade by human expert. And we go from the human effort-driven system to data-driven system, where the rules are implicitly or explicitly learned from the data. EBMT introduced a very important concept called translation memory. It's called example-based machine translation, where parts of the translation could be used in new situations. So, for example, the capital of India is Delhi. भारत की राजधानी दिल्ली है. Now, if there is a new sentence, the financial capital of India is Mumbai, then lot of the previous sentences translation can be reused in this sentence. की राजधानी है. की राजधानी है, you can take from the previous sentence and plug into the new sentence for this translation. The only thing you have to deal with is the financial, the word financial, which you can pick up from another sentence. The financial condition of the organization is good. Okay, संस्था की आर्थिक स्थिति मजबूत है. So financial being arthik is learned, is picked up from another sentence. So all this is actually was going towards preparing the ground for SMT. This kind of part translations became the phrase table in statistical machine translation. So phrase table construct and alignment, they were covered in Saurav's lecture, but these are detailed and involved topics. We should spend a little more time on the creation of alignment, word alignments, and from word alignments, phrase alignments. Okay, phrases are pre-translated components. Okay, let me just ask Anshul and Harsh, am I audible? Slides are visible?
Yes, sir, you are audible and the slides are also visible.
Okay, fine. Let me go ahead. Well, so language divergence is the main challenge of machine translation. This is a very practical problem which needs to be solved. And we have already discussed a Vauquois triangle in detail. We, in the last class, we just showed an example of transfer, which is very clear in terms of its operation. If we take the sentence, John eats bread, we know that in Indian languages, John, the subject, will remain in the beginning of the sentence, as in English. Bread and eats, they will exchange position, interchange position. John roti khata hai. So this can be achieved by taking the verb phrase in the sentence and interchanging the positions of V and NP. So that will take care of the syntactic order of the target language sentence. John bread eats. Now you do the word substitution. John, bread roti, eats khata hai, and you obtain the Hindi translation. Now this activity or this action of interchanging positions of V and NP is a transfer step. Okay, so let me repeat this point. You have to be very clear about what is transfer after all. So transfer is transferring a parse tree from English space to Hindi space. It is transferring the parse tree from the English space to the Hindi space. So the transfer rule is making use of the knowledge that English is SVO, Hindi is SOV. So V and P being interchanged in terms of position is called a transfer operation, and it is a rule-based operation. Okay, it is saying that go to the verb phrase, look under it, V and NP, just change their positions, interchange their position. That's the transfer operation. Okay, now here comes several interesting discussion. In rule-based machine translation, this will be explicitly done. A rule will do this job, this transfer. In statistical machine translation, it will be implicitly done. Eats bread will be mapped to roti khata hai. So there will be this kind of verb phrase to verb phrase mapping. Verb phrase English verb phrase map to Hindi verb phrase. Of course, there will be some probability value. Okay. Um, because it is a statistical probability based system, it can also get mapped to uh, khaya tha, okay, or just khata with some probability. So the phrase mapping also will have a probability of its own. So this is statistical NP. What happens in neural NP? In neural NP, the whole sentence, John eats bread, will get encoded as a vector. And that vector will give rise to another vector or a series of word vectors, which is John roti khata hai. And transfer has been again implicitly obtained. Unlike statistical machine translation, it is not stored anywhere. Or you can say it is stored in the memory of the encoder decoder, okay, which is very difficult to inspect. That's why neural machine translation system or any neural NLP systems are very difficult to scrutinize, analyze, debug, because things are so opaque. So I hope you are, able to see the crucial differences between RBMT, SMT, and NMT. In SMT, the phrase mappings are explicit. They're in the phrase table with probability values. In neural MT, there is no phrase table. The phrase table is implicitly stored inside the parameters of the neural network. Now, let's understand the analysis transfer generation process over the Vauquois triangle with a more involved example. So this is a Hindi sentence, and I'm giving transliteration, gloss, and the English sentence for anybody who has limited knowledge of Hindi. So the sentence is सरकार ने चुनावों के बाद मुंबई में करों के माध्यम से अपने राजस्व को बढ़ाया. सरकार ने चुनावों के बाद मुंबई में करों के माध्यम से अपने राजस्व को बढ़ाया. So this is the transliteration. H1 dot 1 means it is a Hindi sentence. T1.1 means it is a transliteration, T for transliteration. G stands for gloss. We are giving the equivalent word mappings for the Hindi sentence. So Sarkar maps to government. Sarkar government. Ne is an argative marker. It's a grammatical element. Chunav, elections. Ke baad, after. Mumbai, may in. Karon, taxes. Ke madhyam se, through. You see how many ke madhyam se gives rise to only one word in English, through. Apne, it's could have been own. Rajaswa, revenue. Ko is accusative, grammatical element. Badhaya, increase. So this is called a gloss. It helps a non-native speaker of the language to relate to the words and phrases in the source language. Okay, so gloss plays a very important role. Make sure you give all the four forms given a non-English sentence. And then comes E. E corresponds to English. H Hindi, T transliteration, G gloss, E English. So the government increased its revenue after the elections through taxes in Mumbai. So you see, if you look at the gloss, then you will understand how much of transferring activity has taken place over the Hindi sentence. Government has become the government in English. Sarkar has become the government. So one word gives rise to two words here. Name maps to nothing. Okay, Badhaya increased was at the end of the sentence, increased at the end of the sentence, as the gloss shows, has come to the third position in English. Then all other constituents or components are coming one by one at its respective places. Now you can ask, Up to gloss, I understand. I can look up a dictionary, and if there is ambiguity, I'll be assisted by probability values to pick up the right word. If there is sufficient amount of corpus, then these probability values will be authentic and they will help me get the correct mapping. How do I get the positioning of the target language words? Positioning also is learned. Okay, that is the business of the phrase table, and that is the business of autoregression in neural machine translation, which produces word by word the target language sentence. Okay, so let's look deeper into this process of generating the target language sentence. First, we would like to understand what is there in the source language sentence. First, we would like to get the core of the sentence. Core of the sentence is subject, object, verb, or for English, subject, verb, object. The core is the subject, the government. Verb is increased. Object is its revenue. Even the and its are actually qualifiers. The core elements of the sentence are government, increased revenue. So corresponding Hindi words are sarkar, increased badhaya, rajaswa. Sarkar badhaya rajaswa. Apne will come before rajaswa. The will not map to anything in the Hindi sentence. So first of all, we'll take care of the absolutely the skeleton of the sentence, without which the sentence will not be able to hold together. So the core sentence is Sarkar Badhaya Rajaswa. Hindi word order would be Sarkar Rajaswa Badhaya. Now we find that there are additional elements in the sentence. Through taxes in Mumbai, this has an instrumental role. How did the government increase its revenue? Through taxes in Mumbai, that's why instrumental, that's called the case. So through taxes in Mumbai maps to मुंबई में करों के माध्यम से. And then there is a temporal adjunct, additional information after the elections. After the elections should have been चुनाव के बाद. Sorry, चुनाव के बाद. So this correction needs to be done. So these are called adjuncts, additional information, instrumental and temporal. So we'll first take the core sentence from the source, the government. Before this, we have the P0 position. Then the government increase, between them we have the position P1. Increase its revenue, we have P2, and at the end of the sentence, we have P3. So the point is that the additional information, the instrumental group of words and the temporal group of words will occupy positions at these places. And this is a learned task. This happens through learning. Where do these adjuncts or the additional information go? Now, if this is learned, how is it learned? And what is the rule that is used for learning? That we do not know. We know it if it was a rule-based machine translation system, but in SMT, it happens through the decoding algorithm, and in neural through autoregression. But what is the exact rule that is applied? That's not known in case of data-driven machine translation. So now we have P0, P1, P2, P3, these four positions. They are now open for the adjuncts to come in. Adjunct means additional information. So one possibility is after the elections, the government increased its revenue through taxes in Mumbai. So through taxes in Mumbai, the instrumental has gone and occupied P3. After the elections, temporal, this has come before the sentence. But you can take little bit of liberty with these adjuncts. You can move them around. Through taxes in Mumbai remains there, but after the elections can go to the end of the sentence. Okay, so P3 can be occupied by two adjuncts, and which which order will be more preferable, that will be decided by what is called the probabilistic distribution, probability distribution, which is learned from the data. Now, let's look at the Hindi core sentence. Sarkar ne badhaya, the government increased. This is the core sentence. And now the translations of the adjuncts and qualifiers will be inserted here. चुनाव के बाद सरकार ने मुंबई में करों के माध्यम से अपने राजस्व को बढ़ाया. So चुनाव के बाद has been placed at P0 position. And in P1, we have placed Mumbai में, which is a special adjunct, करों के माध्यम से, which is an instrumental adjunct. Both we have placed here. And अपने राजस्व को, that also has been placed in P1. So Sarkar ne badhaya, they hold the fort, and in between the other textual elements are inserted. We could also have चुनाव के बाद मुंबई में करों के माध्यम से सरकार ने अपने राजस्व को बढ़ाया. चुनाव के बाद मुंबई में करों के माध्यम से अपने राजस्व को सरकार ने बढ़ाया. This is another construction. मुंबई में करों के माध्यम से चुनाव के बाद सरकार ने अपने राजस्व को बढ़ाया. This is also another possibility. But what is invariant, you see, in all these variations is that Sarkar has to come before Rajaswa. Rajaswa has to come before Badhaya. That order is not to be disturbed. This is the canonical order for subject, object, verb as the defining syntax for Hindi. Okay, so this illustrated the various considerations which go into filling the positions after the core sentence has been generated. Okay, and this is where we have the main challenge of MT, the language divergence. There are two kinds of divergence, syntactic divergence and lexical divergence. Under syntactic divergence, we have constituent order divergence, adjunction divergence, preposition stranding divergence, movement divergence, null subject divergence, dative divergence, pleonastic divergence. So when did all this work happen? All this work happened during the rule-based machine translation days. Okay, that is when people needed to understand, researchers needed to understand what is what is meant by divergence and what are the different kinds of divergence that exist. So these different kinds of divergence are recorded here through meticulous linguistic effort. And now we detail out all these divergences. The larger category of lexical divergence will come after some time. Constituent order divergence is how the constituents change position in going from source to target language. Jim is playing tennis. So Jim is subject, he is playing is verb, tennis is object. So in Hindi, we find that the object and the verb change position. So Jim, tennis, खेल रहा है, he is playing becomes खेल रहा है. So this is why it is called constituent order divergence. The change, there is a change in the order of constituents. He saw a girl whose eyes were blue. So S, he, saw V, a girl, O, object, Q, qualifier, it is a qualifying clause, whose eyes were blue. So the Hindi order would be, first we'll have to maintain the core sentences order. He a girl saw. उसने एक लड़की को देखा. And then comes in जिसकी आंखें नीली थी. So the question is, can the adjunct occupy any other position? So it can. उसने एक लड़की जिसकी आंखें नीली थी को देखा. That is also allowed in Hindi. So constituent order divergence refers to the change in order of constituents. Now, after you have studied parsing, the notion of constituent should be very clear in your mind. Adjunction divergence is a special case of constituent order divergence. Looking back, you can see that. But it was given a special category mainly because in translation, adjunction divergence really creates a headache. Okay, all this additional information, which part of the sentence will they occupy? So the incorrect Hindi sentence, English sentence, the star indicates incorrect. The living in Delhi boy, Delhi में रहने वाला लड़का. So Delhi in living boy. So this is an example of an adjunct. Living in Delhi is an additional piece of information. So the correct English sentence is the boy who lives in Delhi. And in Hindi, typically you have this wala construction. So the adjunction divergence is exemplified here. The boy who lives in Delhi has been captured as Delhi mein rehne wala. Okay. Then the Hindi sentence here, the English sentence is Ram sent the gift that Mohan likes. Ram sent the gift that Mohan likes. So Ram sent send the gift is the core sentence. That Mohan likes is adjunct, additional information. So राम ने मोहन को पसंद आने वाला तोहफा भेजा. राम ने वो तोहफा भेजा जो मोहन को पसंद आया. राम ने वो तोहफा भेजा जो मोहन को पसंद है. All these variations are possible, but all of them refer to adjunction divergence. How is this additional piece of information dealt with? They are dealt with differently in the two languages. PP adjunction divergence, where the adjunction is through a preposition phrase. He called me to his house. So to his house is the adjunct here. He called me is the core sentence. How does Hindi deal with this? उसने मुझे अपने घर बुलाया. So अपने घर to his house has come and sat in front of the main verb बुलाया. He called me to his house. This is the adjunct to his house. See how it has moved from the end position to a position inside the sentence. उसने अपने घर मुझे बुलाया. This is another construction. Preposition standing divergence is a very typical English language phenomenon. Which stop did John go to? Which stop did John go to? So here, the word stranding means there is a distance between the preposition and the noun it should be attached to. To the actual sentence is to which shop did John go? To which shop did John go? But English allows preposition stranding. Which shop did John go to? So to can go to the end, separated from shop. So किस दुकान में John गया? So this may cannot go to the end in Hindi sentence. So preposition stranding is not allowed in Hindi. It is a matter of divergence, and it's a structural divergence. English allows preposition divergence, preposition stranding. Hindi doesn't allow. The null subject divergence is interesting. Languages of the world are divided into two categories broadly: null subject and with subject. English doesn't allow any sentence where the subject is absent. Okay, so long ago there was a king. So this there is the subject, but it has no semantic role. It's semantically backwards. It is called a pleonastic. So null subject divergence. बहुत पहले एक राजा था. Okay, so there is nothing corresponding to there in the Hindi sentence. So Hindi has given a null mapping for the English subject there. In Hindi, you can say जा रहा हूँ, where the subject is dropped. So this is a case of null subject. In English, you are not allowed to say am going. You have to say I am going. The subject needs to be mentioned. English doesn't allow any construction without a subject. Then pleonastic divergence is this. It is raining. So this it is called a pleonastic. It has no semantic role. It has no meaning actually. So in Hindi, you have to say बारिश हो रही है. It doesn't map to anything. It is like null subject divergence, but the null subject divergence is more general than pleonastic divergence. Pleonastic divergence is a special case of null subject divergence. Now, subject divergence can drop a pronoun. जा रहा हूँ. मैं is not necessary. Okay. Then lexical semantic divergence is concerned with words and their meanings, words and phrases and their meanings. There are these categories: conflational divergence, structural divergence, categorical divergence, head swapping divergence, lexical divergence. So all these are intricate work from the era of rule-based machine translation. We do not worry about them when you have huge amount of data and use statistical or neural machine translation. But when we look at the output of the machine translation system and want to understand the error, if there is a pattern in the error, then we might come back and say, oh, the machine translation system doesn't deal with a particular kind of divergence properly. Maybe it does not deal with pleonastic divergence properly. So that is insightful. And then you can take some measures, maybe increase the data with lots of pleonastic divergence examples. Then this problem will disappear. Okay. So conflational divergence, structural divergence, categorical divergence, head swapping divergence, lexical divergence, these are called lexical semantic divergences. So conflational divergence is where we have conflation, a word giving rise to multiple words in the target language. Jim stabbed John. Jim ने John को छुरे से मारा. So stabbed has become छुरे से मारा. This is called conflation. Conflation means expansion. So stabbed has been expanded to छुरे से मारा. Can there be deflation? Think on this. So in English, you have a number of words which maps to one word. So think of those examples. Conflation divergence, structural divergence. Jim entered the house. Jim घर में प्रवेश किया. So entered has become pravesh karna. Okay, so entered the house. Pravesh entered has become pravesh karna. For some reason, okay, this is given the name structural divergence. So it is actually a form of conflational divergence, but structural divergence is a special kind of conflational divergence. Now, interesting thing is Jim घर में प्रवेश ही किया. So you can introduce he, all these particles here. So it is not possible to do so in case of English. So Jim घर में प्रवेश भी किया. Jim also entered the house. So you have to keep also outside entered. You cannot insert it inside entered. Whereas if entered has become pravesh karna, then that the particle can enter that structure, okay, which came from enter, which is pravesh karna. Then categorical divergence. Here there is change of part of speech. They are competing. Competing is a verb. वो मुकाबला कर रहे हैं. So competing has become मुकाबला करना. One word compete has become a combination of two words, one noun, मुकाबला, and then karna. Similar is the case for advice. Advice in English is one word. Salah dena is the Hindi corresponding Hindi group of words. So वो मुकाबला कर रहे हैं. This is called categorical divergence. Here there is a change of part of speech. Competing is verb, मुकाबला is noun, and then कर रहे हैं is a verb group. In categorical divergence, you can have demotional and promotional divergence. Demotion means the part of speech category goes from a higher level entity to a lower level entity. What is a higher level and lower level entity? The highest level entities are nouns and verbs in part of speech hierarchy. Adjectives and adverbs which qualify nouns and verbs respectively are at a lower category. Preposition, conjunction, all these function words are at the lowest category. So categorical divergence of demotional kind is illustrated here. It suffices. यह काफी है. So suffices is a verb, highest level of category. काफी है. काफी is adjective and है. So adjective and an auxiliary verb. So there has been a demotion from a verb to an adjective, and then an auxiliary verb. You can have promotion also. The play is on. On is a preposition here. खेल चल रहा है. चल रहा है is a verb. So from preposition, which is the lowest part of speech category, has moved up to verb चल रहा है. This promotional category. Then another kind of lexical divergence is this. Hindi. जॉन जबरदस्ती घर में घुस गया. जॉन जबरदस्ती घर में घुस गया. जॉन forcefully house in entered. John forcefully entered the house. That is one translation. But another translation, which is more idiomatic, is John broke into the house. Okay, broke into captures this jabardasti ghusna. Okay, so this is given the name lexical divergence. So this is a listing of the different categories of language divergence which need to be negotiated for effective machine translation. Let's move to a very important topic called machine translation evaluation. Machine translation evaluation started becoming important after lots of groups from various places in every country started claiming that their translation was the best, and evaluating machine translation output is a painstaking job. You have to intricately observe, where is the verb gone? Are the prepositions, postpositions correctly mapped? Is the morphological suffix properly given? Are the case markers good? Intricate task. Lots of effort needed there. So then the community started thinking about automatic machine translation evaluation. We'll come to automatic evaluation, but let's look at some of the underlying principles of machine translation evaluation. There are three kinds of evaluation. Operational evaluation. Is machine translation system A operationally better than empty system B? Does empty system A cost less? Okay. So since machine translation is a very practical field, and there is huge need for translation in all kinds of fields, in parliaments, in legislative assemblies, user manuals, foreign services, diplomacies, tourists, everywhere you need translation. So translation is a practical need. Now the question is, if there are multiple translation systems, which one should I buy? Sure, the one that costs less and gives equal accuracy, of course, is very nice if you're comparing two systems. So cost is one of the operational parameters. Typological evaluation. Have you ensured which linguistic phenomena the machine's translation system covers? This is the most difficult. Which linguistic phenomena the machine translation system covers? Maybe the machine translation system do well for rotational divergence. Okay, so whenever you have stabbed, you're going to chure se marna, it falters. It doesn't produce chure properly or marna properly. So this is an example of malfunctioning with respect to conflational divergence. But this is a very, very difficult criterion to ensure. Declarative evaluation. How does the quality of output of a system fare with respect to that of B? So this is where the automation has happened mostly. How does the quality of the output of a system fare with respect to that of B? So this is a comparison of the quality. Now, one might think that, well, the moment we say quality, doesn't it involve human judgment? Yes, it does, but I'll show you through discussion on Blue Score that there is a surrogate for human judgment. That surrogate is n-gram-based Blue Score. Okay, so again, does the system cost less? Does A cost less than B? That is easy to determine from the charges involved. What linguistic phenomena A handles which B doesn't? Difficult. And the quality of the output are the comparable. This is through glue score. Now, since human judgment has been used extensively for estimating or measuring the quality or comparing the quality of empty systems, two parameters, two concepts have ruled the evaluation field for a long time, and they are still there even now. Adequacy. Adequacy is called comprehensibility, fidelity, faithfulness, and fluency. These are the two parameters, adequacy and fluency. Adequacy is also called comprehensibility, fidelity, and faithfulness. So, assigning scores to specific qualities of the output. Fluency is how good the output is as a well-formed target language entity. So if I'm doing English in the machine translation, and if the verb has not gone to the end for a declarative sentence, then I'll give a low fluency score. If the postposition, ko, for example, has not come, Ram ne sham ko dekha, Ram ne sham dekha. If ko is dropped, then again I'll penalize on the fluency front. Adequacy is how good is the output in terms of preserving the content of the source text. So Ram saw Sham, Ram ne Sham ko dekha. Sham ne Ram ko dekha will get a low adequacy score because the meaning there has changed. So adequacy and fluency are two very important guiding parameters for evaluation of translation. Now you can see why adequacy is also called faithfulness or fidelity. So Ram saw Sham, Sham ne Ram ko dekha. The target language sentence has been unfaithful to the source language because the seer is Ram and what he saw is Sham. In the Hindi sentence, that role is exchanged, which is not allowed. Comprehensibility corresponds to does all parts of the sentence appear in target language sentence with adequate mapping. And fidelity, of course, is again another name for faithfulness. Okay. So this is adequacy and fluency, and we should mark them carefully in our mind. So fluency corresponds to syntax, adequacy corresponds to semantics, pragmatics, all these things, sentiments, and so on. Now, let us make some reference to LLMs. Large language models have been extremely successful in terms of fluency. If you interact with ChatGPT, you will never notice any kind of syntactic problem. The sentences are all fine and well constructed. So much so that people have started using a ChatGPT for text correction. So I would write something and I'll leave it to ChatGPT to improve. So it improves it very, very admirably. Grammarly also does that job. It keeps on giving suggestions for forming the sentence better. So fluency, today's natural language generation systems are very comfortable dealing with fluency, at least for English. And as a student of NLP who has been doing this course until now, you will recognize that fluency is a matter of language modeling. When I'm doing auto regression, that is, I'm producing the next word based on whatever has been generated before, and also the input. Then the highly accurate probability distribution ensures fluency. Okay, so in a Hindi output, automatically Ram ne will be produced and not Ram when the verb is in past tense and is transitive. Ram ne Sham ko dekha. So this ne will be produced because of the power of auto regression. So we see that language model, the concept of language model is really very, very robust with respect to fluency ensuring. Adequacy, no, we know the very frequently referred to well discussed problem of hallucination. So any departure from adequacy is a departure from faithfulness, fidelity, comprehensibility, and that sometimes is manifested in the form of hallucination. So Ram ne Sham ko Ram saw Sham, Ram ne Sham ko dekha. If we have Sham ne Ram ko dekha, these days, in today's LLM terminology and parlance, we say the machine translation system is hallucinating. Okay, it is hallucinating, saying that it is Sham who saw Ram and not Ram who saw Sham. So this is a case of hallucination. So lack of adequacy sometimes is manifested as hallucination. Lack of fluency hardly occurs in large language models. Okay. Then we have this very old philosophical concept, the concept of form content dichotomy. It's an ancient philosophical concept. Consider a pot of milk. Milk has the form of the pot, and pot has the content as milk. Adequacy refers to the content, fluency refers to the form. If the sentence is well formed, then we say that it has high fluency. So adequacy and fluency we exemplify with further sentences. Suppose the English sentence is I am attending a lecture. मैं एक व्याख्यान बैठा हूँ in this sentence. I, one, lecture, sitting. So this is not well formed, but the meaning is conveyed. See? So it is adequate. That means it is transmitting the meaning, but it is not fluent. But if I say मैं व्याख्यान हूँ, then it is fluent, but it is inadequate, unfaithful. I am attending a lecture. I am not the lecture. So मैं व्याख्यान हूँ means I am the lecture. So here the adequacy has been violated. In the first example, fluency has been compromised. Now, adequacy and fluency are measured in a scale of 1 to 5. This is the traditional practice. In CFIELD, we have done lots of machine translation evaluation as requirement of large machine translation projects. And this adequacy and fluency being in the scale of 1 to 5 is almost universal. I think everywhere you will see this is the range which is adopted. Where 1 means bad, 2 means mediocre, 3 means good, 4 means very good, and 5 means excellent. So this is how the sentences are given the value, okay, between 1 to 5 in that scale, 1 to 5. 3 is good, 4 is very good, 5 is excellent. So all machine translation systems strive to remain in the range 3 to 5 as per human judgment. And in fact, the Bhashini project, of which we are a part in IIT Bombay, we are dealing with 10 languages there. The requirement from the ministry is to have 60% of the test data to be in 3, 4, and 5 range. Of course, it will be excellent to have all 100% in 3, 4, 5, but that doesn't happen, as we know. It will also be excellent to have everything in the category 5. That also doesn't happen. So the requirement is to meet the criterion of 60% of the source language sentences to have a translation which is in the category 3, 4, or 5. Now, since we have a lot of experience on human evaluation of translations through adequacy and fluency, there are some interesting facts we observed. We found that native speakers are particularly keen on the correct usage of morphological variations and function words in the language. So Rahul ka behan, even though it is adequate, it is conveying the meaning, whose sister is who. Instead of Rahul ki behan would be critically penalized. So native speakers are very intolerant of morphological mistake. So instead of मैं जाऊंगा, if I write मैं जाओगे, then the fluency score will be very low. Native speakers do not tolerate morphological mistakes and function word mistakes. Similarly, मेरी किताब पढ़ता है, which is a morphological mistake. Rather than मेरी किताब पढ़ती है, because Mary is a feminine gender for subject. that also will attract high penalty. And we also found that if a person has given low score on fluency, the person gets biased towards evaluation of adequacy also. Somehow it is an impression that if somebody has fluency problem, that somebody will have meaning problem also, adequacy problem also. So that's why we have found it very difficult to maintain the strict compartmentalization between adequacy and fluency. We have, even if we tell the human evaluators repeatedly that keep fluency and adequacy independent of each other, do not be biased by one for the other. They are not able to do so. So this is an important observation, and we found high correlation value between fluency scores and adequacy scores. So these two things let us remember. Native speaker evaluators are intolerant of morphological mistakes and function word mistakes. And they also tend to penalize adequacy if the fluency is bad. And the opposite is normally not seen. If the adequacy is low, fluency is not given low value influenced by adequacy. Okay, so now let me introduce quickly the blue score in about 10 minutes time. We'll continue the discussion going forward, which, as I said, will lead to discussion on a very important topic of hypothesis testing, which applies not only to LNP, but whole of machine learning. Blue score is used in any kind of natural language generation situation, question answering, summarization, machine translation, paraphrasing, everywhere the output is a piece of natural language text. So this is a case of natural language generation, and blue score is used there. Adequacy and fluency also are used for any kind of natural language generation. So QA, summarization, MT paraphrasing, they also use adequacy and fluency. Only adequacy fluency is human created, blue is automatic. What does blue need? Let us see. Human evaluation is the ultimate yardstick. Any automatic metric that we propose should correlate very well with human evaluation. So any automatic evaluation must correlate well with human evaluation. So blue is an automatic metric for machine translation evaluation. It has been in existence since last 20 years. And it has satisfied reasonably this requirement of correlating well with human evaluation. So that is the strength of blue. It's a very simple measure, deceptively simple. And blue, when it was first proposed, actually raised the eyebrows of experts. How can it work really? No. How can such a simple thing work for a very complex thing like evaluation? So the experts were actually baffled. But blue has stood the test of time in spite of all kinds of criticisms. People have said that for morphologically strong languages, rich languages, blue is not good. We also have a paper called Blue for Blue. That means the cause of concern for blue, where we have criticized blue, saying that for morphologically rich languages, blue is not good. But then what happened was that for morphologically rich languages, subword blue is used. So we apply byte pair encoding, break the morphemes apart from the corpus, and then apply blue. And again, blue comes back with a lot of strength. Subword blue is good for human level correlation. So except in case of high morphological complexity, in which case we have to use subword based blue score. So blue has stood the test of time. Why so? We'll see that very soon. An allied point is IAA. IAA is Inter-Annotator Agreement. Human evaluation is the skyline, but human evaluation is subjective. Okay. So if I take the adequacy and blue score from a single individual, that's not enough. We should take from multiple people and then see the annotation agreement. And for that, there is good statistical measure. Cohen kappa for 2 evaluators, Fleiss kappa for multiple evaluators. So we must have multiple evaluators and compute their inter-annotator agreement either by Cohen kappa or Fleiss kappa. So how is translation performance measured? The closer a machine translation is to a professional human translation, the better it is. Okay. The closer a machine translation is to the professional human translation, the better it is. So therefore, we'll have to compare the machine translation output with the human translator's output. So clearly now we are pointing towards a case of reference translation, what is called reference translation. So given an English sentence, let's say, there will be human translations, more than one maybe, which are Hindi sentences, and the machine's output will be compared with the human translated sentence. So it is essentially a matching task. A machine has produced a translation. This will be matched against a human translation. So a corpus of good quality human reference translations is created. As you can see, this also requires time, energy, and money because human labor is involved. So in the Bhashini project, of which we are a part again, we have created 1,000 test sentences. Okay, and we call them a test corpus with buckets. So first of all, we have taken these test sentences and created buckets. That means we have first got length buckets, 0 to 10 words, 11 to 20 words, 21 to 30 words, and 31 and more. So these are the 4 length buckets: short, medium length, longer length, and very long length. So, so these are the 4 buckets which are according to length in Bhashini project. And then we have also divided them according to domain: administrative sentences, agriculture sentences, tourism sentences, law sentences, and so on. So if I take one single domain, let's say I take law. Under law as a domain, I'll have these 4 buckets of short, medium, long, and very long sentences. This is how the test corpus is created, and it's meticulously done. Okay. Now, if you remember, one of the criteria for evaluation, that is how many linguistic phenomena does the machine translation system capture and do well. So here there is, you might come back and say that you have these buckets which are according to domain and buckets with respect to length. We have observed that as the length increases, more and more linguistic phenomena step into the sentences. So length, it is not possible to increase the length by introducing new language phenomena. So that's why this bucketing with respect to length and domain is quite good. And these 1,000 test sentences are given to all the consortia in the country, and they are serving as good benchmark for evaluating machine translation systems. So this is the paper, which is the landmark paper for a machine translation evaluation. This is where Blue score was introduced in 2002. And as I mentioned to you, lots of people are surprised by the effectiveness of this score. And reevaluating the role of Blue in machine translation. So lots of papers came after Blue was being used extensively, criticizing or examining its nitty-gritties. We also wrote this paper in 2007, which is well cited. Some issues in automatic evaluation of English in the machine translation: more blues for Blue. More blues means more headache for Blue. So the preliminaries are as follows. There are what are called candidate translations. These are translations returned by an empty system. Reference translation, perfect translation by human beings. Now, nothing is perfect. Human beings themselves may introduce error. They can have biases and so on. We have seen it repeatedly. So that's why it is a good idea to have multiple reference translations and compute the Blue score based on those translations. So goal of Blue is to correlate with human judgment. So Blue score is formulated in step by step. So let me introduce step one. Other steps we'll do in subsequent classes. So suppose I have this English sentence, I had lunch now. There are two reference translations. मैंने अभी खाना खाया. मैंने अभी भोजन किया. Now you see, for any natural language sentence, multiple translations are possible, where structure varies, vocabulary varies. Both translations are, both references are good, and they can be adapted. Now a machine produces the first a candidate. मैंने अब खाना खाया. मैंने अब खाना खाया is the output of the machine. This is the candidate translation. Now we'll see how the blue score is computed. First, we have to find out unigram matching. So in candidate translation, there are 4 unigrams. मैंने अब खाना खाया. 4 unigram. Unigram means a single word. So out of these unigrams, how many are matching in the reference translation? मैंने has found a match in मैंने here. Ab doesn't find a match. Khana finds a match in khana. Khaya finds a match. Now you have to search in all references. Okay. So matching unigrams is 3. Matching bigrams. Bigrams is combination of 2 words contiguous. मैंने अब, this bigram doesn't match. अब खाना doesn't match. Khana khaya matches. Okay. So then matching bigrams are 1. So we compute what is called unigram precision. How many unigrams out of the candidate translation are correct? Here in candidate 1, 3 out of 4 unigrams are correct. So 3 by 4 is 0.75. Similarly, bigram precision is 1 by 3. There are 3 bigrams. मैंने अब खाना खाया. So only khana khaya is correct. So 1 by 3. So bigram precision is 0.33. Let's take the candidate 2 and another machine translation output. Another machine has produced a output. This output is not good. मैंने अभी lunch ate. So lunch ate is not translated. Here, what is the unigram precision and bigram precision? We have 2 matching unigrams, मैंने and अभी. Bigram precision is 1. Sorry, bigram matching is also 1. So there are 4 unigrams. So 2 by 4 is the unigram precision score, which is 0.5. And 1 by 3 will be the bigram precision score. Okay. So this is the step 1 for finding out the blue score. We have to get the unigram precision, bigram precision, trigram, quadrigram. Typically, we stop at n equal to 4 and then compute an average of these precisions. Which average? It is not arithmetic average. We know that arithmetic average has this problem. Arithmetic average gives me a wrong impression if one of the values is large. Harmonic mean is also not appropriate here because harmonic mean gives preference to the lowest value. So that's why geometric mean is chosen. And geometric mean, log of the geometric mean is used. As we go forward, we'll understand these things. So fine, we will